Our second talk this afternoon is from Daniel, and he's promised to, I don't know, give us some ChatGPT outputs to laugh at or something like that. But anyway, he's going to talk about multi-step reasoning via curriculum learning. All the buzzwords are there. Let's go for it.
All right, thanks, Rob. Thanks for the organizers for putting on this great workshop, for the invitation. This is joint work with a bunch of fantastic collaborators, Yishuan, Ishan, Alberto, Alex, Jason, and Denny. We're all roughly in the same area of Northeast. So this is about multi-step reasoning and curriculum learning. It's motivated a lot by, as you might guess, these really large language models or machine learning models, where we've started to see that they have these kind of very interesting capabilities. One that I'm sure maybe these are all kind of familiar to everyone now, but one that really kind of stuck with me when first learned about it was this phenomenon that people called in-context learning, which kind of changed the game on how we use machine learning these days. Instead of collecting data, running scikit-learn, and getting your classifiers, now you just skip that. You just give it the training data directly to the language model, input-output pairs, and then just ask now I want a prediction on this new point. The language model is supposed to make the prediction for you. So kind of avoid doing offline training, learning, and just the language model does the learning for you. Okay, so that was already quite amazing, I think, in 2020, but now we're not even satisfied with that. Now we would like to do even crazier things, I think, like this, what people call multi-step reasoning. Really old idea, goes obviously much older than this, but this is when people started to say that, oh, maybe large neural nets might be able to do this for us. Now, we hope that they will, you give it a description of a theorem you want to prove, and then it proves your theorem for you. This clearly requires a lot of complicated reasoning to do. I think we're starting to get some understanding or some hints as to how these large machine learning models are able to do some of these kind of amazing feats. At the very kind of cartoon level of what in-context learning is, you have a prompt where you give it input-output pairs, whale 1, dog 1, frog 0, shark 0, bat 1, owl 0, wolf. So what's the answer for this one? What should the next token be? Based on this picture, obviously these are very similar. Say, well, it's probably 1. And you might have thought that, okay, well, one way to do this is that, oh, clearly they figured out that I'm just trying to figure out is it a mammal or not. But really, it's more like nearest neighbor learning. I think what's happening is that we have some reasonable like word vector embeddings of words, and you just need to find what's the last kind of in the context of the prompt, the language model, was the word vector for wolf kind of look most like, and among all the word vectors here, it was probably the dog one, at least according to this cartoon of word vectors. And I just output what followed dog in that case, which is the 1. Okay. So I know this is not exactly how all of in-context learning works, but I think it's like reasonable first cut explanation for how it might happen.
Explanation or something that has been verified by inspecting the mechanics of how it's...
So this particular mechanism is something people have identified, that this is sort of what's happening in a lot of some small-scale models, also some larger-scale models. Whether it's exactly nearest neighbor, definitely a lot more happens to get for this thing to output I guess positive here. Some more processing has to happen, not just like one vector for this entire description. But I think this is kind of a reasonable cut explanation for how in context at this very basic level works. Multi-step reasoning, whether you think it's language models are doing a good job at this or not, I think it's clearly something that I think sounds a little bit more interesting and potentially more challenging. So actually, I was going to give it a nice example. Like one thing I like to do with these new language models is like try to get them to solve like these word puzzles that come up like in NPR and New York Times. See if they can kind of do these things. And I often find that they do need some kind of multiple steps of reasoning and kind of similar ingredients that we'll talk about here. This is a very cartoon, very simple challenge for a demonstration of multi-step reasoning. So you have some passage from a story, or here's about some characters. John plays football, a bunch of other things that people play. And then you also say that NFL game is on Sunday. And then finally there's a question at the end, what day does John play? And there's a lot of kind of things going on here, but there's kind of two features of this that I want to highlight. One is that the prompt itself provides you some information that helps you answer this question, that helps the language model make a good prediction. Here's that, well, John is somehow associated with football. Here's that John plays football. NFL games happen on Sunday. Not generally true, but sort of true. But then there's some information that you need that's not in the prompt, which is this what we call parametric knowledge. Like football is like the league that plays football is the NFL. Okay. So somehow, a large machine learning model, in order to solve these problems, would have to be able to combine contextual knowledge together with this kind of parametric knowledge that you don't see in the input, but maybe you learn during pre-training. Okay, so what is it that we want to do as theoreticians to think about this phenomenon of multi-step reasoning and how language models can learn it? We want to have some way to formalize what's happening here. So we defined a very simple type of multi-step reasoning, kind of inspired by that example, and then kind of want to ask like the usual question. Can we represent the solution to multi-step reasoning? Can we learn those solutions from training data and so on? Okay, so what did we actually do in this work with all these wonderful collaborators we did roughly last year? We defined a very simple concept class, just in the way that you would think about statistical learning or pack learning. The concept class is what we call k-fold function compositions. I'll make it very precise what this is in a bit. So I thought that this, this was inspired by a lot of prior work on people trying to understand how multi-step reasoning might happen in language models. But once we have this definition of a concept class, we can do all these learning theory things with it. How do we represent it? Turns out you can represent it very efficiently, exploiting all the power of transformers using small depth transformers. And then you can ask learnability questions. And what we found is that actually there's good reason to think that you cannot efficiently learn this concept class, at least in this so-called statistical query model. But there's something new. Turns out it'll be very kind of almost trivial sounding. That with something called curriculum learning, even really simple things like gradient methods should be able to learn. Okay, so that's the plan for this talk. So feel free to stop me with any questions throughout. Okay, so let me define for you this concept class of k-fold function compositions. Okay, so kind of do it through the example, and then I'll give the formal one. So I want to define a concept class, so it should be something that you potentially want to be able to learn. So the input is going to be kind of capture what the concept is supposed to do is supposed to process things like this and give you the correct answer. Okay, so what is in the input here? Well, we have two things. You have context information, and then you have the question. Okay, so what is the context information? The context information here is that you've listed a bunch of people's names and tell you what sports they play. Okay, that's really defined for you some function. And there's another function that tells you a bunch of leagues of sports and on what day of the week do they play. Okay, and then finally there's the question. I should say question is here is John is one of the names, and I would like you to tell me on what day of the week does John play. Okay? And what's not explicitly in the part of the input is the information that you need to learn from data is this parametric knowledge, which is this mapping from sports to what leagues play these sports. Okay? Okay. And like I said, this is you can think of this as the answer here is supposed to be Sunday. Is that right? Okay, Sunday. And the way you got to Sunday is that what happened is that you composed these two functions, sigma with and sigma 2. But before sigma 2, you put pi, the hidden information in the middle. So you compose these three functions together, and then you apply to the question x.
I have a silly question. How does the LLM distinguish between which football you're talking about? Like, is it the American football or the European one? I mean, okay, in this case, it might be a silly question, but in some context, a word might mean something.
Yeah. So I don't know. I assume word vectors have something to do with it, and that absolutely good question. How a real model deals with this, you might use more information, not just like a single word or a single token. It might get some estimate of what the exact sense of the word football is. Is it used in an American sense or a non-American sense or some other sense? Yeah, a great question. But yeah, here we're just abstracting out a lot and tons and tons of details. Okay, so this is actually inspired by a lot of kind of ways people have tried to think about multi-step reasoning in the context of language models and transformers. I started thinking about it when we were looking at what problems are hard for transformers, or seem to be hard for transformers or other kinds of large neural models. And kind of the problem that kept coming up again and again is some kind of pointer chasing problem. If you've heard of like the K-hop reasoning or K-hop induction head, this is kind of all in that coming from there. Okay? And so a lot of people have studied these types of tasks in the context of, can transformers do this? Can RNNs do this? And so on. And here we're trying to look at it from the perspective of learning. Okay, so that's the at a high level, or sort of like example. Let me kind of formalize this. It'll be kind of the clear, obvious thing. Instead of just 3 functions that we compose together, there'll be 2 K functions that we end up being composed together. K of the functions will come in the context, part of the input. So here we have a K tuple of functions, sigma 1 through sigma K. Okay? And then there'll be a question X that we want to ask about. The parametric knowledge is also a K tuple of functions, okay? Pi 1 through pi K. So each pi I is itself a function. Okay? So this is the thing that you would need to learn. And the target function that we're talking about is where you kind of compose the pi's and the sigmas in this interleaving fashion. So you first do pi 1, then sigma 1, then pi 2, then sigma 2, and so on. Okay? And then take that function and apply it to x.
Interleaved exactly like that? Or can some be null? Or?
Yeah, so if they're not interleaved, then let's say all the pi's came first and then all the sigmas, then it turns out to be much easier. There's really just one pi to learn, and there's only one sigma that sort of matters. But actually the sigma, that part's fine. That's still interesting, but there's only one pi to learn. So what makes the problem hard is that is the interleaving aspect of it. Okay, so this is, yeah.
I had a related question to that. So do all target functions have to be this way, in the sense that maybe for some question you have to interleave it in this way, and for some questions, there is also like the number of steps and like how many, like how does the interleaving happen could be potentially different for different questions? Is that included in this kind of definitions? Or?
That is not captured here, so that's a more broader class of tasks that you might hope to learn to solve. Here, we're just doing this particular case.
Will have this.
Yeah, these are the only target functions that we'll be considering. Okay, there's one thing that is slightly more general that I'll say at the end, but I don't think it's not really addressing your issue. Okay, so this is our concept class. And to make everything easy for us mathematically, is that we'll assume all of the functions, all these pi's are in fact bijective functions. Okay, so really, it's you have permutations, and you're composing these permutations together. Okay, so now that we have the function class, which I'll always call F in this talk, we have these questions. Can machine learning models represent these concepts in this function class? Of course, we might be interested in things like transformers. Okay? Can transformers efficiently represent these concepts? And then learning, right? So can we efficiently learn these concepts from data? Okay? And ideally, if you want to hope that this is relevant to practice, these should be learning algorithms that kind of look like what learning algorithms people use in practice are. Okay, so what's address the representation question first. So the first issue is that there are a lot of neural architectures out there, and not all of them kind of will be able to kind of represent these concepts when I claim to be like a nice, efficient manner. And it's kind of maybe not so obvious why I think this is not efficient or not satisfying, but until I tell you the next part. But recurrent nets with kind of smallish hidden state size. What that means is that the recurrent net will process each input to the problem, like each word or token, one at a time, and all the while maintaining some hidden state. They cannot represent these kinds of concepts unless the hidden state size is enormous. So that's the main bottleneck with recurrent neural nets. So these will not be. I'm just asserting right now. This kind of lower bound tells you that this is not going to be a great concept, or sorry, neural architecture for learning or representing these concepts. It turns out the same thing is kind of true when you look at just one-layer transformers. For strange reasons, one-layer transformers are also kind of equally weak in some sense as recurrent nets or kind of low-memory models, very related to what Nati was talking about earlier this morning, unless you have lots and lots of these so-called chain of thought steps. So if you don't remember or care to know what chain of thought steps are, you can just say that there's no chain of thought steps, and one layer transformers cannot do this efficiently either.
So when you say no RNN with hidden state size can represent F5, that's okay. But then if you want like something that mimics it with epsilon accuracy.
Yeah, if you have some error, we did not look at the dependent. If you're okay with some, only approximating it, we didn't look at that.
But loosely speaking, like, is it how bad is it?
I would guess that it's still pretty bad. Maybe like an epsilon shows up in the front here or something. So for any kind of, unless you allow like epsilon to be, sorry, it should be somewhere else. I don't know where, but if, epsilon, unless epsilon is pretty large, I think you'll do a pretty bad job. Maybe it's like 1 minus epsilon or something. Okay, but why do I say this is bad? Is because when you look at multi-layer transformers, these can exploit parallelism in a very nice way to solve, to kind of represent these concepts very efficiently, in the sense that you just need the number of layers, kind of the number of sequential steps that they need to do is only logarithmic in the number of functions you're trying to compose together. Okay. So here's if you haven't seen this kind of result, this is not, there's a lot of results kind of that look a lot like this. But any one of these concepts, you can represent it using just a log k layer transformer and it kind of exploits parallelism in kind of the natural way that you expect transformers to be able to do. There's one kind of weakness of this result, which is that we use kind of a pretty large embedding dimension, like a fixed one that, for the entire function class. This is definitely a weakness, but in some sense it's necessary for the kind of statement that we have here. Okay. This is, if you haven't seen this before, it's kind of inspired by a lot of prior work that have been looking at, how transformers kind of exploit parallelism in computation. There's a very nice paper by Bingbin, Liu, and many co-authors on finite automata simulation, and we use, very similar ideas for in a previous paper. Basically, the idea is that when you want to look at how you compose these functions together as part of the input, the first step will kind of just encode the first step. You don't have to worry about exactly how transformers do this, but in some sense, the first stage of the transformer is to just kind of do the individual compositions of sigma 1 with the hidden parametric knowledge pi 1, sigma 2 gets composed with pi 2, and so on. And then you start building up a binary tree. So you compose these two things together to get some other function. Okay, that's by definition that thing. You compose these two things together to get some other function, and so on. There's some other things that I guess are being computed here, but don't need to be. And then you compose even further, and kind of keep doubling in sense the length of your composition with every layer. And that's why you end up with just log k layers. Okay, so in this sense, I think it's quite reasonable to think that if you have kind of very if you have these kind of parallel architectures, you can really exploit the ability to do all this processing in parallel. They kind of don't depend on each other, and you can kind of solve very kind of deep chains of multi-step reasoning reasonably efficiently.
Is there some information for what the input embedding dimension helps with?
Yeah, so the reason for the input embedding dimension being kind of large is that we don't know how to analyze in the training and the learning part. We don't know how to talk about learning when you have nonlinear functions in between the transformer. So we don't have any of those in our transformer. And also, if you want like a fixed embedding dimension that kind of works for all functions simultaneously in this class, you somehow need enough parameters in your model to even distinguish between all the different functions in this class. And so this is roughly the number of parameters you need. So you better have something related to that number. Okay. The number of parameters, what the number of functions in here is like n factorial to the k, I guess. Something like that. So the log of that is like kn or something.
The question is that why can you only combine two functions?
Why can't you do even more? I think this is roughly a limitation of the transformer architecture that kind of looks at pairs of things at a time. The intuition, I guess, it would be that transformers kind of operate in a pairwise fashion, and that's why. But without getting into the details of how a transformer works, maybe we can talk after. Any other questions?
The arrows, like they are just combining that way. You're not learning like a path through this.
Yeah, so here there's a very fixed pattern how things are being combined. That is like the one place where like there's an extension of where you might do some slightly more complicated composition where maybe you don't know the exact order. Maybe pi 1 sigma 1 comes first, and then pi 3 sigma 1 and pi 7 sigma 7. So maybe there's some that would make the arrows kind of look some funny way. I think all of our positive results kind of would naturally extend to that case. Yeah, if we're here, just pretend it's you did the first ones and the second ones and the third ones. Okay, good. So in terms of learning, okay, so that was all just about representation, nothing about learning. The first question you ask when you want to talk about, can we learn this concept class efficiently is, how much data do we need? Forget computation, so it's just the sample complexity question. But here I kind of already hinted at the answer, is that this is a finite cardinality concept class. Nati reminded everyone this morning about, if you have a finite class, it's very easy to learn, at least statistically, how much data do you need? Just log the cardinality of the concept class. If you just do the counting correctly, I put an O tilde to hide any things, maybe some other logarithms I missed, but it's, I think, k times n is the right thing. So if I have k times n IED labeled examples, just finding a consistent hypothesis based on for this data will be enough, and that will pretty much identify the correct function very, very accurately. Okay, but that's ERM, and you could kind of squint eyes and say like, oh, gradient descent basically does ERM and so on, but maybe that's not quite true because at least our understanding is kind of limited by how well we understand whether ERM solved these kinds of optimization problems, and there's reason to believe that actually ERM does not do this in a general sense. So we have this what seems like what's called a computational statistical gap, in that to achieve this kind of sample complexity of just k times n, the only algorithm we know is just enumerate all functions and try them all. So it's very slow, very large time complexity, and every efficient algorithm we could think of for doing this better than just brute force search would need a much higher sample complexity. Okay? And so the question is this like a real gap, or is it just our inability of coming up with good algorithms? So we have some evidence to suggest that it's real, and that comes in the form of what's called a lower bound in the statistical query, or SQ model. Is Ilias here yet? Okay, maybe Ilias would be the expert on what SQ model is. Here's my cartoon interpretation. So SQ is like a theoretical model for thinking about certain classes of learning algorithms. And you kind of constrain on what kind of access of information the algorithm or learner has. And so the learner never gets to see data. The learner just has to ask questions about the data. And someone else kind of has access to data and gives you answers about those questions. Okay? And so this is formalized in what's called the stat oracle. So this is the stat oracle, and here's your learning algorithm. You'll ask some question, which is just some function about a single data point, single labeled example, and gives you some bounded number between -1 and 1, let's say. And what you receive as the answer to that query is just the average value of that function up to some error tau. Okay, so you can ask these questions. Oracle gives you an approximate answer, and you do this adaptively. Okay. So this abstracts away a lot of things about what learning algorithms do with data, but a lot of algorithms can kind of be thought of as working in this model. Not quite true, but I think it's reasonable to start here. And then the main question in complexity is how many queries do you need to make, and how small can this, or how large can this tolerance be? And what we proved is kind of a very basic, kind of typical type of lower bound in the SQ models, which says that every SQ algorithm for learning this concept class, we want to achieve kind of small error, average error rate, and this will be under like a nice distribution, just a uniform distribution. Either needs to make a lot of queries, either n to the some constant times k queries, or has to ask at least one query that at very, very small tolerance. Have to be almost very accurate answer, n to the minus some constant times k. So the way you usually interpret this is that, okay, well, the number of queries you make is at least a lower bound on how much time your algorithm is going to take. So either you need at least this much time, okay, or you need enough data so that you can answer a very low tolerance query where the tolerance is very, very small. And so a rough heuristic would be that, well, if this like the error you want to have in your estimation, you better have like inverse that many samples, so like n to the k samples. Okay, so good. So that's kind of bad news. But finally, the positive result we have is maybe kind of obvious in retrospect, is that you can get around this by just kind of changing what information you get during training time. So the kind of observation is that even if you forget about learning, but just in terms of like representing these concepts, they seem to be harder when k is larger. You need to compose more functions. The task is harder, and so you need to spend more. At least the representational complexity is higher. Somehow, in some sense, these tasks are the harder tasks. Okay? And if we somehow could learn from not just the hard tasks, but also easy tasks, maybe our life would be much better. And that turned out to be the case. Okay? So if you also have examples where you not just learning from these k-step reasoning problem, but just like one-step reasoning problem, life would be great. And that's sort of what happens in our positive result. Let me just show you empirically what happened. We trained a transformer to try to solve the k-hop problem, where k is, I think, 16 in this case. And then I'm not showing you what happens when we just try to only do it here. I'll show you that in the next slide, or 2 slides from now. But I'm measuring the performance on the one-hop data, where tasks only have 1 step of reasoning, 2 steps of reasoning, 4 steps of reasoning. And this step here is not step in like this sense, the number of hops, but the steps of gradient descent. So how many iterations or epochs of gradient descent do we do on the transformer? And so we very quickly learn to solve all of the 1-hop problems, and then we very quickly learn to solve all the 2-hop problems, and so on. So empirically, even just from with gradient descent or with gradient descent like algorithm, somehow it's easier to learn to solve the easier tasks, and then you progressively solve the harder and harder ones. Okay? And so that's roughly what we can prove formally. The exact theorem statement, and exactly what we mean by curriculum is a little complicated, maybe not terribly interesting. But this reduces the runtime and sample complexity down to something that's polynomial in both k and n. And even with like a practical looking algorithm. I won't say it's actually gradient descent, but it's something that looks like gradient descent.
Is this a like cartoon or like a real plot for toy task?
This is a fake task.
But it's like a real plot of running the algorithm.
Oh yeah. This one is real, but it's okay.
It looks too.
Maybe I'll just skip the. Let me skip this. Is there a way to skip directly?
Going back to Nati's talked about end-to-end versus chain of thought learning, and is this sort of like kind of related? Like you're sort of learning. I'm showing you a one-step example, which is one step of a chain of thought, and I'm showing you a two-step. So I'm doing these end-to-ends, but of different lengths, and so that's also kind of a way around things. Is that the way to think about it? I'm not sure that I'm making the right connections.
Yeah, that's another way that you might have learned these things, where instead of just showing you, in the particular example, I don't just show you the answer, but I show you all the steps along the way, like for computing this answer. That's what chain of thought learning, that's what Nati talked about. Here, I don't necessarily do that for any single example. It's just that I have a lot of easy examples where you only needed one step of reasoning. And I also have a bunch of easy-ish examples where you only need two steps of reasoning. But in any example, I don't show you the whole chain of reasoning or anything like that.
If we just did K-hop with chain of thought, would it be better off with that? Or is this equally good in terms of getting whatever?
I think if you had chain of thought training data, it would you would also be able to learn in poly, K, and time. It's just maybe your transformer would be used to do this thing sequentially. You compute each, you compose thing kind of sequentially. Perhaps you'd first compose one function, then two functions, then three functions. Here, you kind of just do it in this logarithmically many steps, which is perhaps better.
Yeah, I was wondering if you know if this may be related to like hierarchical feature learning. So if the underlying features have a hierarchical structure, then gradient descent also goes in.
Yeah, I'll say this at the end, but yeah, it's very much related to a lot of things like staircase functions, things like this. Yes. Yeah, great question. Yeah, we'll skip the details of exactly what I meant by curriculum learning, but it's sort of what you might guess is okay. Let me just show you this plot, like a real simulation. So what I showed you with a fake version of gradient descent that's just easy to prove theorem about, we actually just simulated, this data with, and we made up some like natural-looking encoding of the data, and then just tried to train like a realistic transformer using a real gradient descent algorithm like Atom. Or a very small toy case, but it kind of reproduces what we kind of expect from the kind of clean setup. So here what I'm showing you is, again, on the x-axis, the number of training epochs or training steps, and then the y-axis is my error rate or loss. So if you don't use any curriculum learning, you just only train on K-hop data. K is pretty small here, 4. It just never learns. Okay. I think we didn't have so much compute resources, and a colleague from Microsoft recently told me that just train for way, way longer. Eventually, it will go down. But we didn't do this. But with the curriculum data, and this is a very nice case of curriculum training, it's just that we have a bunch of examples, and we mix them all together. 1-hop training data, 2-hop training data, 4-hop training data. Just throw them all together and just train on that with regular Atom, whatever that is. And then you can evaluate how well you do on the easy tasks, the less easy tasks, the hard tasks. And it's again this behavior where you seem to learn to do the easy tasks very early on, and then later you learn the slightly harder ones, and then last you learn the hardest tasks. Yeah, so that's with curriculum. Okay, let me just wrap up. So, this I think is a nice example of how these kinds of multi-step reasoning problems can exhibit the difficulties that we see in a lot of other learning problems, where, for instance, you have these computational statistical gaps where, if you wanted to be super data efficient, this seems to be computationally intractable. But if you have more data, perhaps you can get away with you can do this in polynomial time. And to really kind of subvert this, you should kind of not just like say, okay, there's this gap and we'll just deal with it. You should find ways around this, or I said bridge, but maybe I meant to subvert the computational statistical gap to find better sources of training information. In this case, is curriculum learning. And it's definitely related to a lot of other prior works that looked at curriculum learning for other kinds of learning problems, like structured polynomials, where the polynomials are built up in some very nice way. Parity has also been kind of suggested as a nice test bed for this kind of curriculum learning. There's a lot of works on showing this. I think there's a lot of directions. This is kind of just our first cut at this, looking at this question. I think there's a lot of interesting direction for future research that hopefully we can discuss. We designed our positive results are like the simplest curriculum that we could think of. You first train with 1-hop data, then 2-hop data, and then 4, and then 8, because that just mirrored exactly how our construction would work. We also just said, oh, you can also do this if you just mix all the training data together, and that also seems to work. But surely these, this is just like the first thing we thought of. Maybe there's much better ideas here. And this kind of multi-hop reasoning problem, this k-fold composition task, it's like the simplest kind of problem where you make multiple steps to arrive at the answer. Clearly, you could also ask, how do I, any algorithm, many interesting algorithms take many steps to compute the final answer. And you can ask, how well can we train transformers or whatever machine learning model to do this kind of algorithmic reasoning? And maybe it's most likely it's going to be very hard to just do this from random examples of input-output pairs. But maybe there are interesting, teaching curricula for doing this. And so it's very nice work out of UCSD, looking at this from the point of view of teaching complexity. That I think could a nice direction for research when we want to think about curriculum learning. Okay, that's all I wanted to say. Thank you very much.
Going back to the empirical kind of results and connecting it to the theory. So what is happening? It's just sort of ignoring the longer reasoning things in the early stages of training, or why isn't that actually screwing it up?
Yeah.
If you know what I'm trying to say.
Yeah. So why is it like in this particular case, one of the curriculums that we have, you have a mixture of easy tasks with hard tasks. And you might think that, oh, I have all these hard tasks, that might mess up my ability to learn the easy tasks. At least in our analysis for this particular problem, you don't kind of get any training signal from the hard tasks until you learn to solve the easy tasks. And so what has happened is that, even though you have all these data together, you kind of are forced into this scenario where you first pretend you only have the easy data, and you kind of nail how do I do one step of reasoning, and then
basically the gradients coming back from those things are sort of just
noise
that average out and affect.
And that's very particular to our setup, and in a real problem, who knows exactly what, but that seems to be one effect that could be coming into play.
Because normally when people do this curriculum, they will do this progression, right? Only the easy problems that not. Because I wonder if that's really important or not in other real world things, or if you just throw it all in.
So in our case, like why is it interesting to be able to do with this with just a mixture of all the tasks is that you might not know in a real problem what are the easy problems, what are the hard problems. If you have, but in our particular case, even having this mixture, throwing them all together, you automatically first learn to do the easy things and the hard things. But you're right, if you have some information about what's easy, what's hard, and you don't have this magic cancellation I mentioned, yeah, this would definitely would seem like a very natural thing to do instead.
If the target is like hop 8 curriculum, how are you going to construct like a hop 1, hop 2 to help the learning, or just enumerate all the curriculum?
So
Yeah, I'm just saying, if there's no like a hop 1, hop 2 curriculum, how are you going to directly learn hop 8?
how do you just directly learn hop K?
Yeah.
Okay, so I mean, empirically, what Akshay told me is that you just keep training and eventually it learns. You just have to train for much longer. I don't know how you did this, but he works at Microsoft, so they can do it. If you don't care about doing this with gradient descent, there's other algorithms you could do. You could like embed it, kind of try to solve it with polynomial regression, embed it in high enough space, and then you could just do regression, and that's very easy. But you definitely spend like n to the k time doing this.
This is very similar to a staircase, like leap complexity.
Yeah, so I don't know how to view this exactly as like a leap complexity problem. Now that I said these words, that you could just pretend this is like a polynomial, like a high degree polynomial that you need to learn, maybe this is also potential for doing that. I wouldn't think that it has the leap structure, otherwise we probably would not have proved this SQ lower bound. But yeah.
Okay, well, let's